Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from University of Brighton, a survey of generative categories and techniques in multimodal generative models. Since late 2022, large language models have become the public face of AI. But human intelligence isn't just about words. We see, hear, move, and interact in a rich, multimodal world. This paper steps back and asks, how did we get from text-only models to systems that can generate images, music, video, and even human motion from text prompts? In this video, we'll walk through the key architectures, training strategies, and trends that power today's multimodal generative models. The survey focuses on models that take text as input and generate something in another modality. That includes text-to-text, text-to-image, text-to-music or audio, text-to-video, text-to-human motion, and text-to-3D or object synthesis. The authors concentrate on models and techniques that generalize beyond a single narrow task. Things like core architectures, training strategies, and inference tricks that show up across many systems. To build this map of the field, the authors focused mainly on work published after 2021, but they also include earlier, foundational models when they introduce crucial ideas. They pulled from major conferences like NeurIPS, CVPR, ACL, and ICML, as well as influential archive preprints from labs such as OpenAI, Google DeepMind, Microsoft, Meta, NVIDIA, and DeepSeek. The survey is structured by output modality and by technique, and within each section, models are presented chronologically, so you can see how ideas evolve over time. Under the hood, most modern multimodal generators share a common toolkit. Transformers provide a flexible way to model sequences, whether those sequences are words, image patches, audio tokens, or motion codes. Diffusion models have become the workhorse for high-quality image, audio, and video generation. On top of that, we see methods for building shared representations that align text with images, audio, and motion. And finally, advanced training strategies, self-supervised learning, mixture of experts, reinforcement learning from human feedback, chain-of-thought prompting, and long context training are used to scale these systems and make them more controllable and aligned. The story starts with text-to-text models. Early neural machine translation used recurrent encoder-decoder architectures, but they struggled with long sentences. Attention mechanisms fixed that by letting the decoder focus on different parts of the input dynamically. Then the transformer removed recurrence entirely and relied on self-attention, unlocking massive parallelism. OpenAI's GPT series pushed this to scale with decoder-only transformers trained auto-regressively. GPT-1, 2, and 3 showed that simply predicting the next token at scale yields strong zero-shot and few-shot abilities. Later, models like InstructGPT added reinforcement learning from human feedback to align outputs with user instructions and improve safety, without fundamentally changing the underlying transformer architecture. After GPT-3, multiple labs explored how far scaling could go. Jurassic 1, Gopher, and MTNLG all follow the decoder-only transformer recipe, but push parameter counts and data quality. Chinchilla challenged the bigger is always better mindset by showing that a balanced trade-off between model size and data volume can outperform much larger models. Mixture of experts models like GLAM and Mixtral take another route. They keep a huge pool of parameters but only activate a small subset per token, making inference cheaper. Google's Palm and Palm 2 combine large-scale training with more sophisticated objectives to improve reasoning, multilingual understanding, and code generation. In parallel, we see a split between open and proprietary ecosystems. Meta's Llama series focuses on compute-efficient, high-quality open models that catalyze the wave of community research. Llama 4 moves into native multimodality and adopts mixture of experts to scale capacity while keeping inference costs manageable. On the proprietary side, models like GPT-4 and Gemini extend transformers to handle both text and images, with very long context windows and improved reasoning, though their exact architectures are not fully disclosed. The DeepSeek series experiments aggressively with attention variance, compression, and reinforcement learning to boost reasoning, culminating in DeepSeek R1, which uses a specialized RL algorithm to refine multi-step logical behavior. Text-to-image generation began with GANs like AttenGAN and MirrorGAN, which used attention to align words with image regions and to check semantic consistency. But GANs were often unstable and hard to scale. Diffusion models reframed generation as gradually denoising random noise back into data, leading to robust, high-fidelity images. DALL-E explored a pure transformer approach over joint text and image tokens, while DALL-E 2, Imagen, and MoE combined powerful text encoders with diffusion or masked transformers. Latent diffusion models, including Stable Diffusion and SDXL, moved the diffusion process into a compressed latent space, dramatically cutting compute while preserving visual quality. As image quality improved, the next challenge was control. ControlNet showed how to bolt structured conditions like edges, depth maps, or human poses onto a pre-trained Stable Diffusion model without destabilizing it. DALL-E 3 focused on better prompt following by first training a strong image captioner, then using its detailed captions to train the generator. Rectified flow transformers proposed a simpler, flow-based alternative to diffusion that still scales well with transformers. DeepSeek's Janus framework goes further by unifying multimodal understanding and generation. It uses separate encoders for semantic understanding and discrete visual tokens, then feeds both into a single autoregressive transformer. Janus Pro refines the training schedule and data to boost performance on both text-to-image and image understanding tasks. In audio and music, DeepMind's WaveNet showed that raw waveform generation with dilated convolutions could produce highly realistic speech in audio, but it struggled with very long-range structure. NSYNC and MusicVE introduced autoencoder-style models that learn compact latent codes and hierarchical decoders to better capture musical phrases and sections. OpenAI's MuseNet applied transformer language modeling to symbolic music, while Jukebox combined VQVE compression with transformers to generate full bandwidth audio, including vocals, directly from text and style prompts. Diffusion models also made their way into music. MoE uses a two-stage latent diffusion pipeline to generate multi-minute tracks efficiently, trained on a dedicated text music dataset. Google's Music LM and Noise 2 Music scale this idea up with hundreds of thousands of hours of audio and hierarchical modeling, capturing detailed attributes like mood, instrumentation, and style. Other systems like MusicGen, MuseCoco, and Flux aim for simpler, more controllable architectures, often using a single-stage transformer over discrete audio tokens. Meanwhile, frameworks like NVIDIA's ETTA and Stability AI's Stable Audio Open emphasize open, modular designs and standardized evaluation, helping researchers compare fidelity, diversity, and controllability across models. Video generation started with GAN-based models like MoCoGAN and TiVGAN, which could produce short, low-resolution clips by separating content from motion or by extending frames over time. As in images, transformers and diffusion models soon took over. CogVideo built a large autoregressive transformer on top of a pre-trained text-to-image model, while Fenicky tokenized video into discrete codes and used a masked transformer to generate variable-length sequences. Diffusion-based systems like MakeAVideo, NuaXL, Video LDM, and Emu Video combine knowledge from text-image models with unsupervised video learning, enabling longer, more coherent, and higher-resolution videos. Recent video models increasingly resemble large language models. Lumiere uses a space-time UNet that generates an entire video in a single forward pass, improving global temporal consistency. VideoPoet treats video as just another token sequence and trains a single autoregressive transformer on a mix of text-paired and unpaired videos, unifying tasks like text-to-video, image-to-video, and video editing. OpenAI's Sora goes further with a diffusion transformer that operates on space-time patches, much like tokens in an LLM, and reports emergent capabilities in physical and semantic understanding. Google's Veo and Meta's MovieGen adopt transformer-based or modular pipelines that combine text, image, and video models to produce photorealistic, prompt-controllable content. One limitation of many video generators is that they can look realistic without truly understanding physics. NVIDIA's Cosmos aims to bridge that gap. It uses pre-trained diffusion and autoregressive transformers, plus a curated video pipeline and tokenized representations, to learn the physical dynamics encoded in real-world footage. The goal isn't just to make nice-looking clips, but to support tasks like robotic control, autonomous driving, and spatial navigation. In other words, Cosmos treats video generation as part of a broader world modeling problem for physical AI. Text-to-human motion models translate language, into 3D body movements. TAMOS introduced a probabilistic approach using a VAE with transformer encoders for both text and motion, allowing multiple plausible motions for the same description. T2M GPT and TM2T discretize motion into codebooks using VQ-VAE, then treat motion generation as a sequence prediction problem, similar to language modeling. This improves long-range temporal coherence and enables bidirectional tasks like motion to text. Diffusion-based models like Motion Diffuse and FGT2M push realism further by iteratively denoising motion sequences while also supporting fine-grained control over body parts and time-varying text prompts. Motion GPT takes the LLM paradigm directly into motion. It uses a VQ-VAE to convert continuous motion into discrete tokens, then fine-tunes a language model like Llama using LoRa, which updates only a tiny fraction of parameters. This lets the LLM understand and generate motion sequences conditioned on text, keyframes, or initial poses. Motion GPT-2 refines this idea with part-aware tokenization, separating body and hand movements in a three-stage training pipeline. First learning motion tokens, then aligning motion and language, and finally instruction tuning for a range of tasks. The result is a motion language model that can handle text-to-motion, motion captioning, completion, and prediction within a unified framework. Across all these modalities, a few techniques keep reappearing. Self-supervised learning lets models exploit huge unlabeled datasets, whether they're text, images, audio, or video. Mixture of experts architectures scale capacity without linearly scaling compute. Reinforcement learning from human feedback and instruction tuning help align model behavior with human expectations and safety constraints. And methods like chain-of-thought prompting and long context training extend models' ability to reason over multi-step instructions, narratives, or temporal sequences, crucial for video, music, and motion. Evaluating multimodal generators is tricky. The survey reviews metrics and benchmarks that track how faithfully outputs match text prompts across text, image, music, video, and motion. Tables in the paper summarize chronological trends in faithfulness metrics for each modality, but many benchmarks still miss subtle issues, partial alignment, hidden biases, or safety concerns. The authors argue for richer, multimodal evaluation frameworks that consider not just perceptual quality, but also semantic accuracy, controllability, and downstream task performance. Stepping back, a clear pattern emerges. Transformers and diffusion models have become the shared backbone for text, images, audio, video, and motion. Unified tokenization schemes and shared latent spaces let models treat different modalities more like different languages of the same world. At the same time, the field grapples with common challenges: how to scale efficiently, align behavior with human values, and give users fine-grained control. The survey's main message is that multimodal generative models are not isolated tricks. They're converging into a broader framework for general-purpose AI systems that can understand and interact with the world in a more human-like, multimodal way.